Hi everyone. It's been a very long time since our last tutorial. So in today's one, we're gonna do a simulation of a drilling process, and it will be a coupled mechanical and thermal coupled problem. So we're gonna uh, do the simulation of the drilling and see how that will affect the temperature of the specimen. Okay, so first of all, we want to import the IGS of the drilling bit. So here, from here, file, import IGS, or you can just click Ctrl plus G and click on the IGS file of the drilling bit and open. Okay, try to go for millimeters and then click on OK. So now you have the drilling bit. Okay, the these files you can find it anywhere. If you don't have any specific one, you can just go to GrabCAD and download any drilling bit file. Okay, now we're gonna mesh it. All right, this is a geometry. We cannot do any analysis on it because it's not meshed into elements. So we click on here, element and mesh, auto measure, and try this one, variable size mesh, and let's say the maximum size is 0.5 and the minimum size 0.01 millimeter. From here, select the whole thing, everything, then mesh, then accept. Okay, now you have the red thing. Now the red thing is actually your mesh. Okay, hit the F2 button. Okay, now you see part, you have this one. This is a shell, and here click on assembly tab. You open here, you see you have many things. The first one is the mesh, the one we created just now, and the 1 2 3, the 3 after it is actually the geometry, the file, the thing that we imported from the IGS file. You can see here geometry, 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 so we don't need it anymore. We can just unclick on that. Alright, okay, one more thing I need to highlight here. This one is a shell, meaning inside it is empty. Okay, you click on here, element and modeling, then click on section plane, and if we cut a section here, you will see that it is hollow from inside. Okay, so we off again. Alright, why did I make it hollow? I make it hollow because in this tutorial I'm only interested in the temperature of the specimen. Okay, in real life this drilling bit is solid, meaning inside is not hollow, but we're not interested in the drilling bit, we are interested in the specimen. And speaking of which, now we're gonna make the specimen. So from here, click shape measure, and the entity, our specimen will be cylinder. So click here, solid, cylinder solid. Okay, now you put the parameters of your specimen. The radius, let's say we make it 4, the length we make it 15, this number of element in the radial direction is 20, and the number of element in the longitudinal direction also is 20. We put it 20, and we want it to be in the Z direction, so click on here, direction is Z. Now create and accept. Okay, so now what do you see? This is your specimen, and it is actually clashing with your drilling bit. Okay, and if you look here, you have XYZ. Okay, so this whole thing is actually upside down. You click on control and hold the mouse button, and you can flip it. So actually the real thing is like this. Okay, the specimen is down and the drilling bit, the tool is up. but now it is flipped upside down. So what we're gonna do now, we're gonna flip this specimen, sorry, this tool. Okay, you see the head is up, we want it to be down, so we need to flip it. So how to flip it? You go here, element tools, go to the transform, and now you go to rotate. Okay, so now you flip it first. Okay, so what is the rotation? You can say is X, no problem. The origin, the coordinate, let's say is 0 0 0, and the rotational angle is of course 80. Now we're gonna select the nodes that we're gonna move them or rotate them. We can pick by part, so when you click on this one, the whole part will be selected. Then rotate positive or negative, it does not matter, it will be the same. Now it went down. Okay, it went down, you click accept. Now you see that the tip or the head is pointing down, which is correct. Okay, now after we flip it, we're gonna translate it or move it upward. So click on translate, our direction is Z direction, and here click again, select by part, and put the distance, how much you want this one to go up. We can try 10 first. Translate up, now you see it's moving up. Click more and until you reach where you want. Okay, now it's okay, but it's very far, so you change from 10 to 1. Now you move it down again, make it just nicely touching. Okay, this is exactly on the surface, is not good. We make it, try to make it 0.5, no, 0.1. okay, I think like this is okay. Then click on accept. Okay, now this is the tool and this is the specimen. Okay, the tool gonna rotate in the X, in the Z, around the Z axis, and it gonna move around the along the Z axis, while the specimen will be fixed in XYZ. Okay, so first we start with a simple thing, how to fix the specimen. Okay, we don't want to fix the whole thing. Let's say we just want to fix the button here. Okay, so how we do that? There are many ways. This is an easy way. You click from create entity creation, and you go down here, boundary, SPC. Okay, SPC means space point coordinate or spatial point coordinate, and click on create. Alright, then you see here XYZ, RX, RY, RZ, meaning it's all fixed in all the 6 degrees of freedom. So whatever nodes that we're gonna select now, it will be fixed in the 6 degrees of freedom. Okay, so we're gonna select the nodes at the bottom here. So click by element, click propagate, and click here. Now all the element here, the nodes are fixed. Click on apply. So now you already fix them. Okay, you can choose to show or hide, up to you. Okay, so now we are done with the boundary conditions of the specimen. Now the boundary condition of the drilling. Okay, so the drilling bit or the tool, as I said, the tool gonna rotate and gonna move down. So now we need to define the velocity and the RPM. Okay, so you go from here, this one, keyword manager, click on this one all, and scroll down until you find define. Okay, so here double click here, scroll down until you find curve. Okay, so now we're gonna define the velocity and we're gonna define the RPM. So the velocity, we call it, let's say, feet. You don't need to name the title, but it's always good practice that you always name everything so you know which one is which. Okay, now when time is 0, our feed or our velocity of the tool is 4.2 millimeter per second. Then click on insert. Now we have 1 point. Okay, now when time is 20, the speed is the same, it's not changing. So insert. Now click on accept. So now you have one curve. So if you plot here, you see the curve or the velocity is constant from time equal to 0 until time equal to 20. Alright, now we're gonna define another one. So click on add, and now we're gonna define the RPM or omega or whatever you call it. So let's say is rotation speed. Okay, I used to until now I say is RPM, but LS Dyna doesn't know RPM. The units for this one is radian per second. So whatever velocity that we have, we need to change it to we need to convert it to radian per second. So let's say if you have 100 to 1200 rpm, we need to convert it to radian per second. So how to do that? If you have calculator you can, or if you just like me, you just use the Google. So let's say it is, for example, if it is 1000 as 1000 rpm, then we're gonna put this value. Okay, so let's say we want it to be 2000 rpm. So if it is 2000 rpm in LS Dyna, I need to put this one, which is equal to radian per second. So you just copy here, go to LS Prepost, you click here and paste. Alright, then you click on insert. This is the starting point when time equal to 0. Then when time equal to 20, the velocity or the rotation RPM is the same. So you insert again and you accept. Now you plot, and there is something wrong. You just, let's say, just make this one 2.244, replace this one, make it 44, replace, accept and plot. The value is the same, but still the curve is going down. This one replace, and this one replace, accept. Then why did I click on delete? By mistake I click on delete. Okay, now it's straight line. Okay, accept. The problem just now, because I copy paste from here and you have so many fractions, so that's what make the line not straight. Okay, accept, done. Okay, now we need to define the boundary condition for the tool bit. Okay, now we go to boundary again, click on all here, then go down, boundary, prescribe motion rigid. Okay, boundary condition, prescribe motion and rigid. Why rigid? Because this tool bit gonna be rigid. Okay, as I said, we are more interested in the specimen. So although in real life the tool will wear over time, but in our simulation we're gonna do only one process, and also the specimen is very light material, so we assume that the tool will not wear or anything. That's why we make it as rigid. So click here, prescribe motion rigid. new ID. Let's say this one I call it feed. Now PID, part ID. So which part is the one that's going down? This is part number 2, sorry, part number 1, which is the tool bit. See, I got confused because I did not rename the two parts. Done. Degree of freedom, it's in Z because it's going down in Z. And VAD, velocity or acceleration or displacement. Click here, you see the curve that we defined just now, whether it's velocity, acceleration, or displacement. LS, the program, the software doesn't know, although we rename it. So we have to tell the software what is the curve that we defined just now. So we set the velocity, so just keep it at 0. Okay, now we need to link the curve because we have two curves. We need to link to this command. So load curve ID, click here, so you have the two curves that we defined. So click on feed and done and accept. Okay, so what we did just now, we just defined the feed of the tool. Now the tool will go down with the rate of 4.2. okay, now click on add. We're gonna add new one, and this one is rotation. The part ID, again the tool, which is part 1, will rotate. And degree of freedom, it will rotate around the Z axis. Okay, this tool will rotate around the Z axis. So degree of freedom, you scroll down and you see here Z, rotational degree of freedom. So you click on 7. This one is a velocity curve and it's curve number 2. Then so now you accept. Okay, now we want to define the section of the two materials or the two parts. You try hit on F2 again, click on the F2. So you see now you have shell and you have solid. Okay, as we said before, the tool is shell, is modeled as shell, but the specimen is solid. So now we need to tell the software what is the type of the shell and what is the type of the solid. You click here, keyword manager, and go down to section, and we have many types of sections. So we just click on solid, new ID, or let's start with the shell, and let's say we call it drilling bit section. Okay, it does not matter what is the section, what is the thickness of this shell, because we're gonna, as I said, we're gonna make it rigid meaning it will not deform. Okay, so I make it 0.1 mm. Click on enter. Now all of them will be for 0.1, and then accept. Okay, so we need this command because we want to tell the software what is the thickness of this drilling bit, or what is the thickness of this shell. Now click done. Now solid, new ID, here we call it specimen section, and you just keep it as default and accept. Okay, we need this one for solid because there are many types of solid in the software. We have like 8 element, 8 nodes or 16 nodes, so depends what is the type of the solid element, and the software doesn't know that. So we need to tell the software we need to tell the software explicitly what is the type of the element. We already click on accept, so done. Now we go to material. So what is the material of this tooling bit and what is the material of this specimen? You click on all, go to material, and now we go to number 20, rigid. Okay, So let's say this one is steel. We assume that our, what we call it, we assume that our tool bit is rigid material and it is steel. So click on new ID. Now the density is 7.8 E minus 6. Okay, my units now is millimeter, and the mass is kilogram. So the steel will be 7.8 E minus 6 millimeter cube per kilogram. Now Young modulus will be in gigapascal, 200 roughly. Poisson's ratio 0.3. Okay, now I want to, okay, I accept first, but I want to add one more thing. I want to tell the software that this rigid can only rotate in the around the z axis and can only move along the z axis, meaning I want to fix the degree of freedom of this tool bit. So how to do that? We do from here. Okay, center of mass constraint option. We have two ways how to tell it. So we can put it 1 or minus 1. Now the easy one, I just put it as number 1. Then I click here and you see what number you should put. Okay, so here it says if CMO equal to positive 1, this is CMO equal to positive 1, then if we put it 1 it will be like this, we put it 2 like this, we put 3 it will be like this. And in our case, this tool bit can only move in the Z direction, meaning in X and Y it is fixed, so it is constrained X and Y displacement. So we put here number 4. Now constraint number 2. Okay, what should be the number here? Okay, you see here constraint 2 equal to what? Now if this one is equal to, if CMO equal to positive 1 again, then what should be the number? You see again should be 4, because our specimen only can our tool can only rotate along the Z axis, so it cannot rotate in X and Y, so we put here 4. The rest you don't need to define it, and click on accept. Okay, now we want to define the material of the specimen. Okay, piecewise linear plasticity, and let's say this is bone. We can do the drilling on the bone, so click on new ID. Now the density is 1.64 E minus 6. Young modulus is 16.7 gigapascal. Poisson's ratio 0.3. Okay, sigma yield strength equal to 0.105, meaning 105 megapascal. Tangent modulus, we don't need it. Here, failure strain, meaning at what strain this material will fail, we put 0.9. Okay, C and P, we don't need it. Here we can just put some materials, some points. So the first point 0.105, and then here 0.01. Here we put 0.0125. Here we put 0.91. This stress will be 106, and this is again 105. Alright, what does this mean? We are actually trying to define the stress and strain curve of our material using using linear lines or linear segments. And why we use this one and we did not have this input before for the tool bit, because as I said, the tool bit is rigid, meaning it will not deform. But here our specimen is deformable meaning it can change. I mean, the what do you call it, the elements can change. That's why we need this, we need to define stress strain curve. And this is just a simplified material model for us to define the stress strain curve. Now click on accept. Okay, done. Click on model again. Now click on part. Click again part. Here now you have two parts. Remember, number one is the red one, so this one is actually the tool, and accept. We rename it first. Then the second one is specimen, and accept. Okay, now let's try to remember together. The tool is the red one, and it's what is rigid. So click on this dot. This window will come out. It is steel, rigid steel. This up here is the material model that we select. Done. Section, it is drilling bit section, and the type is shell. Okay, as we agreed, we model it as shell. Done. Now accept. Now go to specimen. Section is this one, solid. The section is solid, and the material is the bone material. Then accept. Okay, why did I do this? Because right now we have two parts, and we have two material that we defined, and we have two sections that we also defined. So now what I just did here, I just linked between the material and the part and the section. Okay, because the software doesn't know which section for which part, and that's why we need to do what we did just now. Okay, if we are doing a normal drilling, then we stop here. We don't need the, sorry, if we are doing normal drilling process, we don't need the next step. The next step, we need to define the material properties of both of them, of both the drilling bit and the specimen. So we need again to go to material. We need to define thermal material properties. So click on all, and I think it should be very down here. We have like a lot of material models. Okay, here, thermal isotropic. So double click on here. Now click on new ID. Okay, now click on new ID, and here we want to define the material properties, thermal material properties. Now this one for the steel. Okay, so here thermal density is same, 7.8 E minus 6. Okay, heat capacity 4600, and thermal conductivity is 460. Now click on accept. Now after that, we need to define the thermal properties of the specimen. Click on add. Now we say it's bone. This is number 2. Okay, fine. The density is 1.64 E minus 6. Okay, and then 1447, and this is 25, and then accept. Okay, done. Okay, again now we need to link between the two thermal properties, the two thermal material models, to the parts. So part, open the part. Now the tool, here click on this one, click on the dot, is steel. It has the steel thermal material properties, and part number 2, it has the bone thermal material properties. Okay, of course these thermal properties you can find it online, and the values that I'm using here not necessary are correct. Okay, then done. Okay, now we need to define some control commands. Okay, so we go up here, click on all, close this one, go to control. Okay, now before we go to control, sorry, we go to contact. Okay, now we need to define the interaction between the drilling bit or between the tool and the specimen. In case we did not do this or we forgot to do this, the specimen will just go through the tool bit will just go through the material, and the material or it will go through the specimen, and the specimen will not be affected. It will not recognize each other. That's why we need to define the contact or the interaction. Okay, so click on contact, then automatic surface to surface. Okay, automatic surface to surface, click new, then we say tool to specimen contact. Okay, now we have two things, we have a slave and we have master. Okay, these two parts, one of them will move and the other one is stationary, so the one is moving, we call it the slave. Okay, so here we have slave ID, but before we can select this one, we need to go here, slave segment type. What is the type of the slave? Okay, is it part, is it one part, or is it a set of part, or is it node, or is it element? We need to specify that first. So here, click here on this blue thing, SS type. You can see 0 means what, 1 means what, and 2 and 3. So we click 3. Why we click 3? Because our slave here, this one, the part that is moving or the elements that are moving are one part. So now here we choose 3, and here we choose tool. Okay, so if this is the slave, then the master should be the specimen. Again, the master type is a part, is not a set of parts, is not a set of nodes, is not a set of element, shell element. Set meaning group in the language of LS prepost. So here 3, and then click on specimen. Okay, now we go down. Here we need to define the coefficient of friction. So let's say we say coefficient of static friction 0.2 and of dynamic friction is 0.1. Of course dynamic is always less than the static, and here we put 20. This one is actually for vibration or oscillation. If we put this one 20%, we put it 20, meaning it will try to damp 20% of the vibration. Okay, now we move down a bit. We have few more things to add. We go down here, no, not here. Okay, you can click here, and this one thermal or T friction, but this is a very advanced one. For this basic tutorial we don't need to bother about them. Okay, but the thing that we need to change is not here, down is actually here. This one and this one, okay, is actually the side forces. So click number 1, and here also click number 1. Okay, this is actually the interaction this is the interface or the interaction forces between the two parts. If we do not put this one, meaning there will be no forces interact. I mean, there will be forces, but the forces will not be somehow calculated. So there will be no friction, no heat from the friction, because there are no friction force. So click on accept. Okay, so far so good, but here remember we are doing a drilling problem. What does that mean? When we do drilling problem, meaning this one, it will rotate and go down here, and the first layer of the element will be deleted, and then it will go down farther down and down. The problem is, if we define the contact like this, like what we're doing right now, then the interaction will be only between the elements that are on the surface of the specimen, meaning if the first layer of the element is deleted, then there will be no more contact between the two parts. That's why in this case the master should not be a part ID. Okay, for this one, the master, we should change it to segment set ID. Okay, right now we did not define any segment set, any group of segments. So if you go click here, the software will tell you, you stupid, you did not define any segment set. So you tell him, okay, fine, I will define it using new entity. So click here, new entity. Okay, so entity creation, create segment. You say specimen, specimen segment. Click by part and click here. Okay, now you see what I want to show you here. Okay, what I want to show you here now is that this one, we call it segment. Now all the segments are selected from all the directions, meaning, let's say we take this one element, all the segments, all the faces of this element are selected. So all the faces of this element will be defined in the contact. So click on apply and then accept, then done. Okay, now we done with the contact. Go down to control. Okay, the famous one, control termination. Control termination, we put it 12 seconds and accept, done. Okay, now we need few extra commands here under the control, because we have also thermal analysis. So first of all, we need control solution, because we want to tell the software that this is a coupled problem. So analysis solution procedure is structural or thermal or both. So we say it is both. Okay, and the rest you can just leave it as default. It's okay. Accept and done. And then the next one, you go down here to thermal solver. Okay, as we know, in the structural solver we have like implicit, explicit. Here also we have few types of solvers. So here you click on 3. This one, let's say it's not linear problem, and this one we say transient analysis, it's not steady state. And solver type is 3, we just keep it as default. and that's all. Then accept. The rest you just keep it untouched. And then thermal step. Okay, you can put it as 0 or you can put it as 1, so you just put it 1. You want the time step to be variable, because if you put it as fixed, maybe the solution is not converging, so an error will be coming out. Here we say it's implicit, and the initial time step, let's say 5e minus 5, and accept. Done. Okay, now done. Okay, one more thing we need to put here is actually control contacts. Okay, why we need this one? Because we need to change one more tiny thing here, okay, which is this one. Okay, calculate frictional energy in contact. The friction is very important here, because from the friction heat will come, and we want to see the heat now, or the change in the temperature. So we change to number 1 and accept. Okay, now click on model. Okay, now almost done. We only, I think we have one more step. Okay, and that step is actually database. So click on all, close this one, search for database. Here, this is database. So first, the standard one is binary D3 plot. So this one we define the intervals of the plot. So 0.03, and click on accept, meaning each 0.03 time there will be a frame of the result coming out. So the smaller this value, the more smooth your video or your result will be, the simulation will be at the end. But of course your results file will be much bigger. Okay, so 0.03 I think is okay. Accept. Now one extra thing here is T print. Where is that guy? T is down here. How come I cannot find it? Okay, you go from here. You can go from here, SQ option. Okay, this is if you want the software to extract or show more result than the default results. So you go down here. Say if you want to find the interaction or the interface force or the reaction forces, you click on this one, resultant interface forces, and here you put, we make it 0.01, so the curve that will come from here will be much smoother. Where is that guy? Okay, T print, tick on here, let's say put the same 0.01 and then accept. Done. And I think that's all that we need. So now Control S and save. Okay, don't save as IGS, just put any name, let's say thermal tutorial.k. Accept, save. Okay, so it is here now. So I just copy this one, I open the ls dyna manager and run new file. I browse, I open the same folder, open, run. Okay, now there is an error. try equation solver 1. I think I put 1 already. Yeah, control. No, not this one. Yeah, I think I put 1 already. Yeah, or I just explained to you guys and I forgot to put it 1. Okay, accept. Then control S, save again. Now if you run, there will be no problem, I guarantee. Okay, then run. Oh, okay, another problem. Error non-positive. Is that right? Why? It is 1. Or I did not save. Save. Okay. Try again. Interesting. This is not error. This is the error. Non-positive definite. Try equation solver 1. Check that the model has a boundary condition that force is out of equilibrium. Remove any reference node. We don't have any reference node. You just check the boundary condition. Okay, feet is moving in 3. Rotation is rotating around the Z. Okay, species set. Create entity. Click on here. Okay, this one is fixed down here, should be okay. Click on material part, sorry, this tool, this is tool, material, 111. Okay, prescribe motion, we check already. Or I think here, control thermal step. This is not small enough, so we put it 6. Accept, then save. Okay, let's see if it works. Still. Try equation solver 1. Okay, accept, done, save. Now click here. Now run. Okay, now it is working. Finally, it is working. So when you go to a thermal solver, here you put solver number 1, not number 3. But this one actually will take a very long time, so you don't want to I don't want to record that very long waiting time, so I can jump straight away and show you how to see or how to read the results. Okay, so this one, it will take many hours, so I just jump here and show you the results. So you close this one, open again, open another pre-post, and here you will have D3 plots. So this one you drag it here, and now you have, click on shift and scroll with the mouse to zoom out. Okay, now click on forward and you can see the thing is going inside. Okay, here is F fast, here S slow, so you may decrease the speed of the animation. Post processing, go to fringe component, and here different things. You are interested in the temperature, so click on the temperature. Okay, now you can see the temperature is rising. Okay, now we are interested in what? We are interested in the specimen, so you just click on the specimen here. Okay, to make this window pops up, you click on the F2. Okay, now you can see the temperature is raising up and up. Okay. There is actually one command that I forgot to put, and that's why maybe I had the error before, and that's actually the initial condition. So here, what is the initial condition? Initial condition of the thermal analysis. So we need to say initial temperature set. Okay, using this one we define the let's say the room temperature. So here we just put 20. Here we don't put anything, we just put 0, so all nodes, all the points are included. So the temperature is actually the room temperature, and click on accept. And I think that's the mistake that I did before. You go to control, solver, change again to the default one, number 3, accept, and then save. This one you don't want, this one also close. Open the pre-post, sorry, open the solver, try now, and it's working. So I think that's all what you need to do. Okay, how to show the results you already know, and how to make the model is as we did. Okay, so the mistake that I did just now is the thermal solver is 3, this is correct, but there is one step that I forgot, is actually to put the initial conditions of the thermal analysis. Okay, so I think that's all for this tutorial. Thank you very much, and hope to see you soon next time. Bye bye.